All right. So some elements have a whole lot of electrons, but not all of them really matter that much. And so we can split electrons into core electrons and valence electrons. The valence electrons are going to be our outer electrons, and so they're going to be the electrons in the highest n value, right? Where n is our principal quantum number. And they're going to be the electrons that do stuff. So they're either going to get rid of, or they're going to either leave the atom, or maybe some more will join them. The rest of the electrons are the core electrons, and then we say these are inert, they're not reactive. And if we think about the way the periodic table is organized, it's organized such that everything in the same column has the same number of valence electrons for the most part. So everything here in column 1 is going to be some value n, right? N will be 1, 2, 3, 4, depending on where you're at. And then it'll be S1. So this only has one valence electron. Everything here in column 2 will be NS2. So we have 2 valence electrons. And then so on and so forth. Right here, we'll have 3 valence electrons, 4 valence electrons, 5 valence electrons, so on and so forth. And so the S block and the P block are what are known as main group elements. And they're generally pretty predictive or predictable. We can know how they behave, and the reason that they behave the way they do is based on the number of valence electrons. So for example, if you think about all the halogens, they're all going to be NS2, NP5, right? Where this N value depends which row you're in, but either way, they have 7 valence electrons. The transition metals and the inner transition metals, the F block, they kind of do their own thing. Things get a little bit more complicated. In terms of general chemistry, we mostly focus on the main group elements, and then transition metals a little bit here and there. And so again, why do elements in the same column behave similarly? Similarly, I can't say that. And the answer is because they have the same number of valence electrons. And if we think about that, that makes sense. The Bohr model is probably the best one to use for this one, right? We said the Bohr model is not quite as accurate as the quantum mechanical model, but it's still pretty good for most things. So if we think about oxygen, oxygen has the electron configuration of 1s2, 2s2, 2p4. And if we were to draw a picture of it, right, we would have some kind of nucleus in here. Then we would have our n equals 1 orbit. We would have 1, 2 electrons located in that. And then if we think about our n equals 2 orbit, both the 2s and the 2p go in that same overall energy level. So while they are in different subshells, their n is still the same, and so they're still approximately the same energy level. And so here we can see that we have 6 valence electrons in oxygen. If you were to take a look at the electron configuration for bromine, you would find that it's argon, 5s2, 4d10, 5p5. And then if we think about how many valence electrons is, remember it's only the highest n. So only the 5s and the 5p count. The 4d doesn't count because that 4 is less than 5. So if we're thinking about how many valence electrons here, we have 7 valence electrons.